So I'm going to discuss observation of supernova neutrinos. Subtitle is past and now, not including future, because the Mark Baggins will talk about the future this evening. I belong to Kamioka Observatory, ICRR, and Kavli IPMU, and I'm enjoying physics at Kamioka. We are celebrating 10th anniversary of IPMU, Kavli IPMU. This year is the 30th anniversary of Supernova 1987A. In February, we had some celebration, and we made a cake. This is a cake, big cake. And this shows the current optical image of the supernova. On February 23rd this year, this cake was made by local Kamioka people. It is really local people. Since it was made on the birthday, so this says in chocolate, Happy Birthday 1987A. Oh, so contents of my talk, why large underground detectors were constructed in 1980s, little history of Kamiokande detector, the observation of supernova 1987A by Kamiokande, IMB, and Baksan, and what we have learned from this observation, then the supernova detectors in the world now, then what Super Kamiokande, this is the detector running now, will measure for supernova. And finally, maybe I don't have time to talk about this, but a brief introduction for Mark Baggins' talk. In 1980s, grand unified theory was predicted. So this is a very famous paper by Georgia and Grasho, 1974. And through those Feynman diagrams, proton decay was predicted. At that time, expected lifetime was 10 to 31 or 30 years. So we expected about 30 to 300 events per 1,000 tons detector per year. That's why few hundred or 1,000 ton class large volume detectors was constructed in 1980s. IMB and the Kamiokande are water Cherenkov detector. Target is water. And the Frejus, Nusex, and KGF, they are iron or something, and so-called tracking calorimeters, few hundred tons of detector size. So this shows the first phase Kamiokande 1 detector, 83 to 84, because of the short of money, detector was very simple. We had only charge readout of 1,000 photomultipliers. The volume is about 2,000 tons. Fiduciary volume was 880 tons. And photo coverage, how much fraction of the inner surface is covered by photomultiplier was 20%. This is relatively high compared with other means IMB detector. Main purpose of Kamiokande detector is because of this high resolution, measure branching ratio of the proton decay. But unfortunately, proton decay was not observed. Even in current Super Kamiokande, proton decay is not observed yet. But thanks to the large photo coverage, 20% photo coverage of the Kamiokande detector, it was found the detector is sensitive to even low energy neutrinos. So the detector was upgraded to solar neutrinos in 1984 to 85. The readout of the photomultiplier signal was upgraded. We upgraded electronics to read out also timing information, not only charge, but also timing information was read out. It improved vertex reconstruction, but accuracy of the vertex position drastically. We made a so-called outer detector layer. So between the rock and the tank, there was not filled before in the first phase of Kamiokande. We made outer detector. This layer was filled with water and absorbed gamma ray coming from the rock. That was made in 1984-85. So the supernova happened when the detector was almost ready for the solar neutrino measurement. This is the optical image before and after explosion of 1987A. Please remember the time, February 23rd. 7:35 is the neutrino time, which I will explain later. But the information of the optical signal was like this way. So February 24th, 5:30 UT, Ian Shelton announced magnitude 5 object on 3 hours observation from February 24, 1:30 UT using 20 centimeter telescope at Las Campanas Observatory in Chile. February 23rd, 9:20, it's about 2 hours after this neutrino time, no optical signal yet. February 23rd, 10:38, almost 3 hours after the neutrino time, first optical observation, magnitude 6 at this time. So the neutrino come first and the optical signal later. It's because this is the time, so in the core, from the core to the surface of the collapsed star, the neutrino travels with speed of light, 3 times 10 to 5 kilometers per second. Shock wave travels through this envelope with the speed about 1/30 of speed of light, 10 to the 4 kilometers per second. Then when this shock wave arrives on the surface of the collapsed star, then the optical signal is produced. That's why neutrino come first and the optical signal come later. In case of type 2 supernova, this time delay is about a few hours to several tens of hours. And in case of 1B or 1C, in case those have very thin envelope, this time could be only several minutes. Anyhow, in case of 1987A, time order of information was kind of reversed. On February 25th, a fax was sent to University of Tokyo. And this is a copy of the fax from the Jid Bradman in Pennsylvania University to Jim Bayer. He was a Kamioka collaborator at Kamioka at that time. So sensational news, supernova went off 7 days ago in Large Magellanic Cloud, 50 kiloparsec away. Now, visible magnitude is 4 to 5. We reach maximum magnitude in a week. Can you see it? U means Kamiokande. This is what we have been waiting 350 years for. We asked Kamioka Shift to send recent data tapes. At that time, no network. Data was transferred, recorded in the magnetic tape, and carried to University of Tokyo. We analyzed the data. February 27th, the data tape arrived at the University of Tokyo, and data was analyzed by me, by the way. Then 28th, Saturday, next day, we found the neutrino event from 1987A. And 1 week later, March 7th, we announced to the world and submitted paper to PRL. So it took almost 2 weeks to, after we get the neutrino signal really happens, to the announcement, it took 2 weeks. I will explain the current status in the data. So this is the signal of Kamiokande data. Horizontal axis is the time in second. Vertical axis is so-called N hit. So for each individual event, how many PMT hits? It's almost proportional to the energy. So usually we observe low energy events. They are mainly coming from the radioactivity in the detector, come from the radon, actually bismuth 214 decay. You see some very high energy events here. We observed around here 12 events within 13 seconds. 11 of them are higher energy event. Higher means more than about 7 point something MeV, N hit greater than or equal 20. And one event here is consistent with the background. The the expected background rate is only 0.2 per 10 seconds. We observe 11, so it's really significant signal. So this is, okay, so this is summary of other observations. Sorry, this particular page is still for the Baksan, but this is Kamioka time, and this is Baksan time because of the inaccuracy of Kamiokande and Baksan time clock. And also IMB observe 8 events. Their time is consistent. So combining those events from Kamiokande, IMB, and Baksan, the time histogram look like this. But please remember that since Kamiokande and the Baksan does not have precise timing information, we adjusted the first event. So like this way. So totally, those detectors observe 24 events, Kamiokande 11, IMB 8, and Baksan 5. And you may see Kamiokande black field data are mostly low energy events, and open circle ones, IMB, higher energy events. One of the main reasons is, of course, the detection efficiency as a function of energy. So this shows the Kamiokande and IMB and the Baksan detectors. The energy threshold of those detectors was Kamiokande 8.5, IMB 28, and Baksan 10 MeV. Because of those threshold of the detector looks like this way. But mostly, initially, somewhat higher, tend to be higher energy events happened, and gradually decreased. So such feature seems to be observed.
What's the volume of Baksan detector?
Baksan is, okay, so essentially 330 tons of target volume. Okay, so what we have learned from 1987A, so there are many papers like this. Horizontal axis is the temperature, and the vertical axis the released new EVA energy, and the Kamiokande, IMB, and Baksan, and combine them. So the result is the total energy released by new EVA was measured to be about 5 times 10 to 52 erg. Assuming equipartition, this means in case of neutrino burst, all species of neutrino, nu mu, nu e, nu tau, and their antiparticles, all of them are released. So assuming each of them has carry same amount of energy, so multiply 6 to this number, we get 3 times 10 to 53 erg. And this binding energy, and compared with the various models of the neutron star and the gravitational mass, essentially neutron star mass, is around 1.4 solar mass. So this is really agree very well with the standard scenario of supernova explosion. So this observation of 1987A proved the standard scenario of the supernova explosion. However, number of observed events was only 24, so no detailed information of the burst process was not observed because of this low statistics. So this is history of supernova detectors. I mean the detectors which are sensitive to galactic supernova in the world. Longest runner is Baksan detector. It started 1980, still running, over 37 years. IMB Kamiokande ran this period, and the LSD detector, there was some controversial argument around, but because of limited time, I skipped that today. Macro detector ran from here to here. Then the large volume detector, it's 1,000-ton liquid scintillator detector at Gran Sasso, ran from 1991 and still running. Super Kamiokande start from 1996 and keep running. Amanda phase and later ice cube detector start to run from, I cannot read well, so around 97. Then Snow ran this time, and now Snow Plus is starting. Cameron ran from 2001, I guess, let me see, 2002. And 1,000-ton liquid scintillator detector, Borexino 300-ton detector, Hero, and the Diabe Nova. So many detectors in the world now running. But although many detectors in the world keep watching starting from Baksan detector in the last 37 years, but no galactic supernova has observed in the this years. The best upper limit was given from this longest runner Baksan detector. Upper limit of supernova rate is experimentally observed by less than 0.074 per year. Of course, it doesn't make much sense, but anyway, limit was obtained. So where are those detectors in the world now? These green ones are liquid scintillator type detectors. Camland 1 kiloton, Baksan 0.3 kiloton, LVD 1 kiloton, Borexino, and Snow Plus is also 1 kiloton detector here. And Nova is a surface detector, but it's a large volume, 14 kiloton. And at least they record all the data, and afterwards, if some other detector gets signal, they can look back the signal and might observe signal. So I put it here. Diabay 0.16 kiloton detector. This light blue super Kamiokande water Cherenkov detector, ice cube is the ice detector. Ice cube has a very large target, but the PMT spacing is very rare, and they cannot detect each individual event, but as a kind of coherent increase of the PMT rate, IMB is ice cube, is also sensitive to the supernova. Other type is target is red, 76 tons of red, and read out by helium-3 counter is HALO in the SNORA. So this table was made by Kate Schorberg in this paper, and list current detectors and future detectors, and how many events are expected in each detector. As you see, Super K expect to observe about, for the 10 kiloparsec supernova, 7,000 events, and compare the others, much more events are expected. And many events may contribute to the ice cube detector, but since it cannot detect each event, it's in the parentheses like this way. And nowadays, there are large volume, ton class, dark matter detectors. They are also sensitive to supernova through coherent elastic neutrino nucleon scattering. This process coherently interacts with heavy nuclei. That process itself was experimentally observed in this year, very recently, by so-called coherent experiment. It was published a few months ago. Because of the coherence, the cross-section is large, and now the large volume detectors are deep 3600 is a 3.6 ton argon, liquid argon detector in SNORAB, 0.1 ton in Gran Sasso, and the Kamioka satellite, we have xenon 0.83 ton of X-mass xenon detector, energy threshold 300 keV, 300 electron volt. And the expected signal is like this way through the coherent scattering, much above the background level. And the expected event rate for 10 kiloparsec supernova, depending on the model, 15 or 3, 4, or 221, depend on the model. So if supernova happens in our galaxy, those detectors are able to detect coherent signal. So what Super Kamiokande do for supernova? As I said, many events are expected. And here I wrote a number of events for two typical models as a function of distance. So in our galaxy, center of our galaxy, 7,300 or 3,100, this kind of inverse beta reactions are expected. And this does not have strong directionality. Some slight directionality, but it's not so strong. The neutrino electron scattering has a very strong directionality, and we expect about 300 or nearly 200 events for this process. So using this process, we can really get direction of supernova. So I showed many detectors in the world, and the Super K is a unique, single only detector is able to detect the directional information. And in the supernova at the LMC is few hundred events. And for the Andromeda, expected number of events is 1 or something rather small. So this shows the suppose supernova at 10 kiloparsec, what kind of time profile we can get by a simulation. So from 0 to 0.3 seconds for the various burst models, and the expected event rate as a function of time, and the mean energy for each timing being is plotted. And the error on each curve is the statistical error of Super Kamiokande. So as you see, Super Kamiokande has very high statistics to discuss which model is correct or not. Also, as I said, the neutrino electron scattering has some directional information. So among almost uniform inverse beta reactions, some excess, you may see excess around here. This is simulation of 10 kiloparsec supernova is expected. And with respect to the supernova direction, and histogram is like this way. So using this electron scattering information, we can get the supernova direction. And the pointing accuracy is as a function of distance is shown here. For example, at the 10 kiloparsec distance, for this Livermore simulation model, 3 to 4 degree of 68% coverage in degree. And Nakazato, this model, for 4 to 6 degree of accuracy. So we can get a very good directional pointing accuracy. So you may think so nowadays, for the gravitational wave case, arrival time of various detectors, the direction direction can be observed. But that, in case of neutrino, that's very difficult because of the number of events in each detector is small. And to do that kind of such triangulation we are saying, millisecond timing resolution is necessary, but the current supernova neutrino detectors in the world are not that much accuracy. That's why this pointing accuracy by neutrino electron scattering by Super Kamiokande is the best way to get the directionality. So what happens to supernova now? Real-time process is always running. It quickly analyzes data. It reconstructs Bartek position and energy and direction. Then this process feeds data to the so-called supernova watch, SN watch machine, and search for timing cluster. And if supernova is really detected, get initial result within 200 seconds after a burst. And the shift person is keep watching those processes running. And if a significant time cluster events are found, send email to experts through the personal computer and portable phone emails. Also send signal to snooze. So then what happens in this flow chart? This is the action flow chart of Super Kamiokande collaboration. So event cluster more than 7 MeV is found. We check whether the vertex position is distributed uniform or not. This means sometimes we have time cluster. This is it is due to the cosmic ray goes through the detector and the so-called spiration happens and many low energy events are produced. So we check that can be easily checked by uniformity of the vertex position in the detector. So if it is uniformly distributed, supernova-like, then we check cluster size, number of events in the cluster. If it's more than 100, we call them as golden alarm. Then we discuss among relevant people with TV conference. And if it is real, send information, including directional information to ATL, GCN, IAU, CBAT, and so on, within 1 hour. So in case of a smaller cluster between 25 and 100, it's called normal alarm. Then in this case, immediately discuss among experts, and the experts hold TV conference and discuss. And it may further proceed through this process. But anyway, like this way. And if less than 25 or the spiration-like case, just send email to experts. Actually, this kind of process happens twice every day. This shows the sensitivity of this process. So this solid curves shows for the sensitivity for golden alarm, and the dotted ones are normal alarm case. And the color indicates the different supernova burst models. As you see, whatever the model is, the Super Kamiokande, this alarm system is sensitive up to 50 kiloparsec. So for the LMC, up to LMC, including our Milky Way galaxy, almost 100% efficient. Okay, so I think my time is almost over. So this is very, very, very brief introduction for Mark Bagin's talk. So we wonder when supernova happens in our galaxy or LMC, but there are many, many stars in our universe. So order of 10 to 17 supernova in our universe. So then those neutrinos must have produced neutrinos, and the expected spectrum is like this way from various contribution from different redshift error in our universe. It's called supernova relic neutrino, and we are now preparing for supernova gadolinium project to detect supernova relic neutrino. And the idea is to dissolve gadolinium and identify anti-electron neutrino event by event basis. This, of course, primary main purpose is the supernova relic neutrino. In addition, it will improve this directional accuracy from 4 to 5 degree to 3 degree, like this way. So I think you will hear more from Mark this evening. Okay, so conclusions. Large volume detectors were constructed in order to search for proton decay. Without this strong motivation, neutrinos from SN 1987A may not have been observed. The observation of the supernova 1987A neutrinos proved the basic scenario of supernova explosions. Super K will observe many events for a galactic supernova, and they will tell us detailed information to reveal explosion mechanism. Super K GD for supernova relic neutrino will start in a few years. Thank you very much.
Thank you.